Hi everyone, my name is Alex Ozdemir, and today I'm going to be telling you about collaborative zero-knowledge proofs. Before we talk about what a collaborative zero-knowledge proof is, we need to understand what a standard zero-knowledge proof is. So for a standard zero-knowledge proof, you've got a prover, and they know a secret witness W that satisfies some property phi, some predicate phi. And what the prover does is they're able to write down a short proof that is written as pi here. And once some verifier checks this proof, there are two important things that happen. First of all, the verifier is convinced that the prover really does know a witness that satisfies this predicate. And second of all, the verifier learns nothing else about what the witness is, which is why this is called a zero-knowledge proof. This sounds like kind of an abstract mathematical notion, and it is, but it's also very useful and powers some very real systems. The first one I'll tell you about is SSH authentication. So whenever you use SSH key-based authentication, what your SSH client does is it proves to an SSH server that you know a secret key, which matches a public key that the server has on file. And it's important that this is a zero-knowledge proof because you don't want to reveal anything about your secret key. That would allow an eavesdropper or even the server to impersonate you in the future. The Zcash cryptocurrency is also powered by zero-knowledge proofs. In Zcash, the way that you spend an anonymous coin is that you show that you know the secret identifier for a coin that has never been spent before. It's important that you do this in zero knowledge because if you were to reveal the identifier for the coin, then someone would be able to trace that coin's lineage and learn something about the flow of money inside the transaction graph. There are two properties that each of these applications have. The first property is that there's some secret information, whether it's a key or an identifier. And the second property is that there's a single party that knows that secret information. And this is why zero-knowledge proofs are applicable, because that single party can play the role of the prover in a zero-knowledge proof. However, there are all kinds of settings where the secret information is spread among many parties. Let's say that you're thinking about money laundering. You want to know whether two entities have some chain of transactions that connect them. In this situation, the transactions are secret data, and they might be in the custody of different financial institutions, different banks. A similar situation is healthcare. In healthcare, you might be interested in showing that across many hospitals, some group of patients is receiving adequate care, but the secret information, the patient treatment data, is split among many hospitals. So in these latter two settings, the secret information is split among many different institutions, many banks, many hospitals, and that means that you cannot directly apply the notion of zero-knowledge proof because there's no single entity that can play the role of the prover. This motivates our definition of a collaborative proof, where there's not one prover, there are many, and the witness is split up into many pieces, each prover having one piece of the witness. The provers collaboratively and interactively construct the proof pi, that can then be non-interactively verified later by some verifier. And the proof establishes that collectively, the different pieces of the witness satisfy some property. Once you write down the definition of a collaborative proof, one of the things that you see is that you need sort of a new definition of privacy. It's not just important that the verifier not learn anything extra about the witness, but it's actually important that other provers don't learn anything as well. To make that a little bit more concrete, let's think about prover 1, who holds witness 1. Prover 1 doesn't want the verifier to learn anything about witness 1, but he also doesn't want the other provers, P2 and P3, to learn anything about witness 1. So how can you construct a collaborative proof that has this notion of security? Well, one natural approach is to build on a different branch of cryptography called multi-party computation. Multi-party computation allows you to securely and privately distribute any function over finite field elements. And so one thing that you might imagine doing is taking a generic MPC algorithm and applying it to a finite field representation of a zero-knowledge prover. So you give the MPC that representation of the zero-knowledge proof algorithm, and then you also give it the witness, and then it spits out a proof. And it just does that, and this totally works, and it's secure. But there's one problem, and the problem is that it's not very efficient. You see, zero-knowledge provers are known for being thousands of times slower than the property that they prove. And MPC algorithms are known for being thousands of times slower than the algorithm that they're securely distributing. And so together, this construction could end up being 1,000,000 times slower than the base property, and 1,000,000 times, that's 6 orders of magnitude. That could be an unacceptable slowdown for many applications. And so the point of our project after we wrote down this definition was to see if we could come up with a better construction than the naive one. So we did a lot of optimization work over the course of the project. I don't really have time to tell you about all of the optimizations that we developed or that we used, but I'll tell you about just one. And this one relates to elliptic curves. So as you might be aware, elliptic curves are a kind of object. So let's say that we've got G1 and G2, which are two different points on an elliptic curve. One of the things you can do with elliptic curve points is you can add them. And in fact, zero knowledge provers, they add elliptic curve points all the time. At least most of them do. And so there's a natural question around how you're going to carry out that addition inside of a multi-party computation. The natural approach is to represent each elliptic curve point as an XY pair of finite field elements, and then use what are known as the elliptic curve formulas for this curve in order to compute the XY pair of the point that corresponds to the sum. The problem is that these formulas are actually quite nasty. They involve a lot of multiplication, and that makes them very expensive inside a multi-party computation because multiplication is expensive inside MPCs. So this approach doesn't perform so well. What we do instead is we do not represent elliptic curve points as XY pairs where each coordinate is shared. Instead, we directly secret share the elliptic curve point. So we take each elliptic curve point and we split it into n different elliptic curve points that sum to the true value. And then we give each prover its own piece of the sum. And when you use this representation, if you want to add to elliptic curve points, then you just add, each prover just adds their part of each elliptic curve point, which is extremely efficient and doesn't require any communication between provers. So this is one optimization that we do. We, of course, use a number of other optimizations as well. The upshot of all these optimization techniques is that we're able to take 4 different base proof systems, 4 standard zero-knowledge proofs, Grot16, Marlin, and Plonk, as well as Fractal, and we're able to transform them into collaborative proofs. And generally speaking, we're able to do this very efficiently. So all of our collaborative proofs incur only a constant amount of overhead compared to their base zero-knowledge proof. They all use a constant number of rounds, or a quasi-constant number of rounds of communication. And for the first 3 proof systems, those based on elliptic curves, we're able to do this without increasing the size of the proofs at all. And then for Fractal, we have to increase the size of the proofs a bit. So we go ahead and we implemented the first 3 of our constructions, Grot16, Marlin, and Plonk. And I'll tell you a little bit about how we did that implementation, because it's kind of interesting. So our challenge is to take a proof and to turn it into essentially an MPC proof, a proof that can be run among multiple provers. Now, our starting point for this was ArcWorks, which is a library that helps cryptographers write zero-knowledge proofs. And the way that you write a zero-knowledge proof in ArcWorks is that you've got a bunch of code that corresponds to the zero-knowledge proof, and it builds generically on top of an elliptic curve or on top of whatever other cryptographic primitives that it uses. And it does this in terms of an elliptic curve interface so that you can swap out the curve. This way, if we ever find a more efficient curve, we can just replace the curve and immediately benefit. So our task is to take this proof and to somehow turn it into an MPC proof that can be run among multiple provers. And one approach, the naive approach, is to just rewrite the whole proof as an MPC. So you can just go through the proof line by line, and for each line, figure out what the MPC, the multi-prover equivalent of that line would be. The downside of this approach is that you have to write a lot of code. These provers are quite large. And another downside is that in order to come up with a collaborative proof that performs well, you're going to have to re-implement all of the optimizations that people have come up with for zero-knowledge proofs. You're going to have to redo all of that yourself. So this sounds like a lot of work, and it sounds like you actually might end up not being so efficient, maybe because you accidentally misoptimize or something. So we take a different approach. Instead of rewriting the proof, we actually don't modify the proof at all. What we do is we take the elliptic curve and we wrap it in what we call an MPC curve. So we wrap it in a new elliptic curve implementation that builds on a base elliptic curve implementation. But instead of just doing curve operations, it implements secure multi-party protocols for every curve operation. So you say add, and it doesn't just locally add, it runs some secure protocol. And then because this multi-party curve, because this MPC curve implements the elliptic curve interface, we're able to plug it in to an existing proof implementation and use that proof implementation essentially unmodified. So this allows us to benefit from all the optimizations inside the existing proof, and it also doesn't require us to modify the existing proof almost at all. We call this technique lifting because we're sort of generalizing we're taking a proof that was intended to run on a single machine, and we're lifting it to a multi-party protocol. So this ends up performing extremely well. We perform a number of experiments in our paper and have performed a bunch of experiments during this project. I'm just going to tell you about one of them. In this experiment, what we did is we varied the complexity of the predicate being checked. So for those who know the jargon, we varied the number of constraints in an R1CS constraint system. And we looked at how long it took us to write the proof under different configurations. So one configuration, the baseline, is that we're just writing a single prover proof. We're using the existing proof system unmodified. That's the purple line. And then all the other lines in this plot correspond to multi-party protocols, where there's some number of provers, and the protocol is designed to be secure against some number of malicious provers that are trying to find out more than they should. And so what we see is that as the number of constraints grow, the difference between the multi-party protocols and the single prover proof, the difference in proving time, gets very small. So for the situations where the number of corruptions that the protocol is secure against is less than half of the provers, this overhead actually goes to zero. So the multi-party proof takes the same amount of time as a single party proof. In the setting where you're trying to be secure against an arbitrary number of corrupt provers, up to n-1 corrupt provers, then the slowdown goes to 2x. So the multi-party computation is only 2 times slower than the base prover. And that might actually sound like a lot, but if you think back to the beginning of the talk, I mentioned that multi-party protocols are typically thousands of times slower than their single machine analogs. And here we're seeing only a 2 times slowdown. So this is actually extremely good performance, really shocking. It's almost 3 orders of magnitude better than what you would expect naively. Okay, so I've been telling you about collaborative proofs. If you've gotten lost, well, I'll tell you what you should take away from the talk right now. You should remember that collaborative proofs are like zero-knowledge proofs, but they support distributed secrets. So they're applicable to situations where the secret data is split among multiple hospitals, multiple banks, etc. The second thing that you should remember is that collaborative proofs are surprisingly efficient. If you want security against n-1 corrupt provers, then this comes at essentially no cost compared to a normal proof. And if you want security against an arbitrary number of corrupt provers, up to n-1, everyone but one is trying to get your secret information, then it only requires a 2 times slowdown over a single prover proof. And finally, I hope that this is a little bit surprising and a little bit intriguing to you. Typically, multi-party computations are thousands of times slower than their single machine analogs. And we're seeing that in the context of zero-knowledge proofs, a multi-prover proof is only in the worst case 2 times slower, which is quite shocking. Okay, so that's the end of my talk, and I guess we'll pause now and see if any questions trickle in. And it may be actually in the meantime, I'll just give a little bit of intuition for why multi-party computation ends up being so compatible with zero-knowledge proofs. Like why is it that this is so efficient? And essentially the thing that's going on here is that multi-party computation is extremely efficient for operations like addition or scaling, so linear operations. And it's relatively inefficient for operations like multiplication. And so what we're seeing here is essentially that zero-knowledge proofs are very expensive to write, but most of that expense goes into computing linear operations, doing elliptic curve point additions, for example. That's an example that we talked about earlier. And so what you see is that because so much of the computational time is spent on linear operations, the multi-party version of the computation can actually be extremely efficient. Okay, so we'll just go ahead and end here. Thank you very much.